Hi and welcome to Lesson 1A in our electrochemistry unit. This is going to be an honors-only extension to half reactions looking at voltage potential. Let's go in and take a look at how this works. We're already familiar with reference table J, which is the activity series. And this demonstrates that some metals are oxidized more easily. In other words, they're more active than other metals. My question to you is, what is the most easily oxidized metal? Do you know? The answer is, of course, lithium. Lithium's at the top of the metals in the activity series, which means it's the most easily oxidized metal in the list. What's the most difficult metal to oxidize? You got it? Yeah, you probably think it's gold, and you'd be right according to reference table J. Table J also has non-metal activities. Non-metals are opposite to metals. The most easily reduced non-metal, fluorine, is up at the top, and then they get less easy to reduce from there. We should also point out that platinum is actually less active than gold. It's just not listed on reference table J. We can use reference table J to determine if a redox reaction is going to occur spontaneously or not. In order for a redox reaction to be spontaneous, the more active metal needs to give its electrons to the less active metal. In order to get a less active metal to be oxidized by a more active metal, you need to put energy in. It's a non-spontaneous process. If this was Regents, we'd leave it right here. But it being honors, we can go in and actually calculate the voltage that's produced when two different metals react in a redox reaction. For that, we're going to use honors reference table D, which is standard reduction potentials in 1 molar concentrations in water at 1 atmosphere and 298 degrees Kelvin. What you see here are different half reactions and the reduction potential that's produced. This lets us calculate the electrical potential or the voltage of a redox reaction. We can also use this table and reverse the values in order to get the voltages for oxidations. Using honors reference table D, we can actually calculate a redox voltage. The total voltage is equal to the voltage of the oxidation plus the voltage of the reduction. To do this, you're going to write the oxidation and reduction half reactions. You're then going to figure out the reduction and oxidation potentials, and then you're going to add them together. In lesson 1, we learned how to use coefficients in half reactions in order to balance the overall reaction. We're not going to do that here. Do not multiply the voltages that you get off of honors reference table D by the coefficients in a balanced half reaction. Just take them as they are. Once you've done this, if you get a positive result, that's indicative of a spontaneous reaction. A negative result would indicate that the reaction would happen non-spontaneously. Let's look at an example of this from page 9 in our Unit 12 packet. Determine the electrical potential and spontaneity of the following reaction. In order to do this, let's figure out our oxidation numbers. There they are. Now let's write the oxidation and reduction half reactions. Our oxidation reaction is chlorine minus 1 becoming Cl2 0, and that's producing 2 electrons from our initial 2 chlorines. Our reduction half reaction starts with Na plus 1 and gives it an electron to produce Na0. Now that we've identified both of those, we can use honors reference table D to figure out the voltages of each. The oxidation of chlorine is going to be the opposite of the reduction of chlorine, and we can get that off of honors reference table D. It's negative 1.36 volts. We can get the reduction of sodium right off of honors reference table D. We don't have to reverse the sign. It's negative 2.71 volts. Adding these together, we get an overall voltage of negative 4.07 volts. That negative sign indicates that this is a non-spontaneous process, which of course we understand because the salt on our tables does not spontaneously revert back into elemental sodium and chlorine gas. A good thing too, as they're both incredibly dangerous to be around. Does this make sense? If it doesn't, write down any questions that you have before we wrap up. Thanks so much for watching this discussion of voltage and how we calculate it in a redox reaction. Make sure you can do the following things here at the end. Make sure that you can determine if a redox reaction will occur spontaneously or non-spontaneously by using reference table J. Also make sure that you can determine the electrical potential, the voltage of a redox reaction, using honors reference table D. If you can do both of those things, you're doing great. If not, that's okay too. Take a moment and write down any questions that you have. You can always leave them in the comments below the video, and you can always get in touch with me. Thanks again for watching. I really appreciate it. Have a great day.